So here's a good example of a very maybe practical kind of question involving proportions. And this, it turns out this is what's stated here is roughly correct for reality. So it's kind of pseudo-realistic, I'll say. It says, given that air drag is proportional to the square of speed, say for a car, I meant to say there, but it says if a car going at 25 miles per hour experiences a drag of 80 pounds, what amount of drag will it have at 55 miles per hour? So how do you answer that question, right? We got three numbers given there. Maybe I could just start guessing what I could do with them. But, the next topic is going to be on problem solving, and that's usually what you don't want to do is just start guessing. You need to have some kind of structure to it, some kind of understanding, some kind of development of ideas here. And I think the way that that's going to look here, and it's part of the reason why I go over proportions in Chapter 1 of this class, is that is definitely one of the tools physicists have at their disposal for understanding problems, structuring them, and figuring out a way to actually come up with an answer. So I've got drag and I've got speed. So maybe if I say that drag is represented by the capital letter D, you have to come up with some variables. You could also say maybe A for air drag, but I decided to go with D. And I decided with capital D, could go with lowercase d. But to me, lowercase d usually represents a distance. I guess uppercase D could too, but whatever. That's the one I chose for air drag. It says is proportional to the square of speed. So my first step here is to translate this language into a more mathematical looking statement. Now, for speed, I could use s, but this is a physics class, and we may as well get used to the fact that physicists like the word velocity. It's slightly distinguished from speed, but it turns out the variable for speed kind of commonly used is v. It relates to the word velocity also being a thing in physics, even though, again, it's slightly different, but they are very closely related to each other. So, in other words, I'm translating air drag being proportional to square of speed, or speed squared, as d is proportional to v squared. That's not really an equation, but it is a statement of a proportion. Now I could go into a whole like, okay, what's the proportionality constant, all that stuff. But the key result that we had from the key concepts page is that if I have some paired values of numbers here, a ratio of d2 over d1 should be equal to v2 over v1 squared. Or alternately, I could also have written that as, oops, I got to move some stuff here. That's some stuff in the way to write this. You could also distribute that square. I'm saying that because this may be simpler to look at depending on how you like to do math, I guess, when we get to some numbers here. So that was the kind of the thing that was given to us on the key concepts page. And it's useful because if I look at this problem and I kind of look at this and I say, well, think about pairs of numbers here, right? Think about air drag paired up with speed. And maybe I'll do it in that order. I'll say like consider like D1 and V1 as like an ordered pair. And I don't always do it with this notation, but I'm going to borrow ordered pair notation from math. Hopefully that makes sense to everybody. And say that like, well, so, okay, for 25 miles per hour, experiences a drag of 80 pounds. So like one way to look at that is I could say that means D1 is equal to that 80 pounds. I'm going to keep units in here just to be clear what I'm doing. Make sure I don't accidentally screw up some numbers or put them in the wrong place, in other words. And if somebody else said V1 and D1 as their ordered pair, I don't think there's any like convention here. So there's different choices, but I want to make sure I stay consistent. And the units kind of help me do that. So I'm saying that, right? That's one of the pairs. And then I've got maybe a second pair, because that's usually, if you have a relationship like what I wrote up here, that's representing two paired sets of values that obey this proportionality relationship. The second one I am given here, well, I'm asked, what amount of drag will it have at 55 miles per hour? So maybe one way of looking at that is for that second pair, I'm going to say the speed value, the value for v, or maybe the velocity value, is 55 miles per hour. But the thing I don't know is what this other one is. That's really the thing I'm being asked for. So if I look at this kind of as my guide, that was the result I had before. Maybe what I could do is I'll just go like this, question mark over 80, and I'll put pounds for that. Whoops, pounds there. Is equal to, so again, that was me just taking these two numbers and doing D2 over D1, and then the other side was V2 squared over V1 squared, so the other side would be 25, maybe I'll put the MPH here, I could probably get rid of it because they're going to cancel out, 25 squared, let me make sure I'm doing this, oh, did I just screw something up? That was actually supposed to be 55, pardon me, So like I said, you want to make sure you keep track of stuff. So I just made a mistake there that's probably very common. Sometimes I'm tempted to re-record the video, but I think I'll leave that there because you might make the same mistake. 55 is really the value of V2, right? And I marked that so clearly, and that's the one that goes on top. In other words, that one's associated with that one there, right? And that means on the bottom, I'm going to have 25. Turns out if you do screw it up, one way to catch that is maybe already know something about the answer before you start. I would expect that the amount of drag at a higher speed is going to be larger. Not only that, but significantly larger. And it turns out if I put these two numbers in the wrong place, you'll get the opposite. You get a smaller result, and that would be a really quick clue that something went wrong. So hopefully we all remember from algebra class, you can kind of multiply things on both sides. So if I multiply both sides by 80 pounds here, then I would get, I'm just going to multiply it, I guess, on the left here. I'm going to put 80 pounds. And then since these two units can cancel out because they're both upstairs and downstairs, they're both hit by squares. Hopefully that's cool for everybody. That means I'm really looking at 80 pounds times 55 squared over 25 squared. And note that if I'd had these two mixed up, 25 squared over 55 squared would make this a lot smaller, but 55 squared over 25 squared makes this a lot bigger, which means maybe I could have skipped all this and just said, you know what, I want a bigger number and just guess and put it in place. It turns out people can do that sometimes. At this point, I might like to go to my calculator. I'm just going to put into it 80 times 55 squared over 25 squared, and the calculator says 387.2, and that should be in pounds. You notice the units because the miles per hour all canceled out. What's really cool actually about this is a lot of times people are tempted to say, hey, it's physics class. We were taught how to convert things into SI units. Let's go and convert all these things into SI units like we were taught to do, right? Think about how much more work that would have been. The cool thing about proportions, I didn't have to do any of that. The units I didn't want automatically canceled out, and it just gave the answer I got. So that's one of the reasons physicists really like using proportions when we can identify them, because they make the units work a lot easier. Let's check our answer. There it is. Looks like we did everything correct.